Let's take a look at some basic ideas of analyzing algorithms. We're going to concentrate on runtime, think a little bit about space, and a bit about some practical concerns that come into play as well. So when we analyze an algorithm, what we mean is that we're given a problem of size n, which we'll discuss what that means in a bit, and a particular solution method. So we have an algorithm in place for solving the problem. The question is how much computational work is required by that method to solve the problem. And computational work can, again, be in terms of the calculations that are necessary, or sometimes we think in terms of the space necessary to solve the problem. So when we talk about runtime, we're not usually talking about actual physical clock time. We are talking about the number of fundamental operations. And we talk about this in terms of the problem size itself. So if we were going to consider a sorting problem where you have a collection, say, of numbers and you want to put them into order, then n in that case is typically the number of elements you have, the number of things that need to be sorted. If you are talking about a mathematical computation, say addition, usually the size of the problem is described in terms of the number of bits needed to write that number, or to write the two numbers that are involved in the addition problem. And so the size of the problem is part of what we have to consider when we are starting to analyze a scenario. And it's not always what we would think of, especially when we're talking about numerical calculations. So the fundamental operations aspect, that depends on what the problem is really doing. And so sometimes a fundamental operation is a floating point operation. Sometimes a fundamental operation is a comparison. Sometimes a fundamental operation is something else entirely. So it depends on the context of exactly what we are trying to measure. Now, typically, the number of fundamental operations can in some way be converted to something that is in terms of clock time. But the issue with the clock time is it depends on which computer you're running an algorithm on. It can depend on what else is running on that computer at the same time. And so clock time by itself is not a good measure. But the number of fundamental operations, sometimes being flops, the floating point operations, sometimes being the other things as we've mentioned. And we describe that in terms of n. So if the number of operations increases, the bigger the problem, then we will describe that in terms of the problem size. If the number of operations stays exactly the same, no matter how big the problem gets, then we can record that as well, and n doesn't really play a role. It's a problem solution method that doesn't depend on how big the problem is itself. The other common measure that we consider, again, is space, and this is just how much storage space is required in order to solve the problem. And this is additional storage space. From whatever we're given a scenario, we have a problem, and then if we need additional storage space to try to solve that particular problem. And so usually what happens is time and space are trade-offs that we have to make. If we want something to run faster, often we need more space. So less time means more space so that we can remember more things. If we don't have the extra space, then often that means things will take longer to run. And so there's usually this balance when we're describing or when we are designing algorithms where we make the decision of which is more important. Are we trying to be faster or are we trying to use less space? because usually in most scenarios we can't have both. When we're analyzing algorithms, we also want to consider a proof of correctness. We want to be able to determine that the algorithm that we're looking at actually does do what we claim that it does. And so these proofs of correctness often, if there are loops involved, correspond to kind of a proof by induction, where you show that if something was in the right kind of position at the beginning of the loop, then at the end of the loop, it is improved, still working toward a solution to the problem. So we're not going to do much about showing proofs of correctness, but we will think about those ideas as we are analyzing certain algorithms. When we're analyzing algorithms, we often consider the best case scenario, but the best case is looking at what is the minimum, or what are the minimum resource requirements needed to solve the particular problem. And often the best case, it just never happens. In real life, the best case situation isn't one that we usually are lucky enough to be faced with. And so we don't spend a lot of time looking at the best case analysis in most situations. What we tend to look at would be the worst case scenario. What are the maximum resource requirements to solve the problem? Because if we know what the maximum resource requirements are, and we have provided those resources, then if we're lucky enough to get a best case, then we know that we're prepared for that. If we only ever prepared for the best case, then the worst case would come along and we would not be prepared for it at all. So again, with the maximum resource requirements, we're saying how much time will we need to solve the problem? How much space will we need to solve this problem? Sometimes, though, we do consider the average case of a problem, that maybe the best case is too rare to happen, but the worst case can also be rare. And so in some cases, we will use algorithms that are really good in the average case. But to analyze the average case typically requires some probabilistic analysis, some other tools that are beyond our scope at this point. So to analyze algorithms and describe what's going on, we're going to look at what's called big O notation, or sometimes Bachmann-Landau notation. And what we're going to do in this case is we're going to consider functions that are from the positive reals to the positive reals. So the domain and the range of our functions are positive. The general theory allows for negative valued functions. We're not going to worry about that because in our case, our functions are in terms of the input is a problem size, and we can't have negative problem size, and the output is going to be like the number of operations or the time. And so in those cases, the output is also going to be a positive number. Often, since we're talking about input sizes and the number of calculations or the number of computations needed, often rather than just real numbers, we're actually focusing on integer values as well. So the set big O of g of x, so g of x is a function, again, a positive valued function from the positive reals to the positive reals. This notation big O of g of x is a set. And it's a set of all functions such that there exist positive real numbers, m and x naught, so that f of x is less than or equal to m times g of x for all x that are greater than or equal to x naught. So the idea here is that we don't really care what happens close to zero, and close to zero can be still far from zero, but we are more interested in what happens after a certain point. So in terms of a limit as x goes to infinity kind of scenario, that once we get big enough on the x values, then f of x is always less than or equal to m times g of x. So anything that is in this set, we often will say, rather than saying that f of x is in the set, we say f of x is equal to big O of g of x. It's an abusive notation, but it fits in with some other kinds of formulas and things that come later, make it a little bit easier. But really what we're saying is if we say that f of x is big O of g of x, we're saying that f can be bounded above by a multiple of g, and it's asymptotically bounded above. So that if we go far enough away from 0, go far enough over in the positive x direction, then once we get to a certain point, the multiple of g is always bigger than the f value at that particular x value. And so if we let f of x be the function 6x squared plus 7x minus 10, we're going to show that f of x is big O of x squared. And so to show that f of x is big O of x squared, we need to find an m and an x naught. Now, we don't necessarily have to find the best m and x naught. We just have to find examples, a particular m and a corresponding particular x naught. So in this case, we can let m equal 7 and x naught equal 5, and then do some algebra. So where these pieces come from correspond basically to having solved the problem backward and then figuring out what values we needed for m and x naught, and then reversing the order to show that things do work. So it looks kind of magical at this point, but it's really solving the problem in reverse to find out what m and x naught would need to have been, and then fixing those so that those are fixed values, and then when we go through the process, then everything works out correctly. So x minus 2 times the quantity x minus 5 is greater than or equal to 0 for all x greater than or equal to 5. You can easily confirm that. And so if we expand the left-hand side, then x squared minus 7x plus 10 is also greater than or equal to 0. Some algebra, and then adding 6x squared to both sides, and this shows that 6x squared plus 7x minus 10 is in fact less than or equal to 7x squared for all x greater than or equal to 5. And so we have our m and we have our x naught, so that f of x is bounded above by a multiple of x squared. Now that may not be the case when the x value is less than 5, but it is the case for everything greater than 5. If we pick a different m, then maybe we can get a smaller x naught, or a different m, and we might need a bigger x naught. But the claim does not say what the m and x naught, that we have to have the best example, whatever that would mean, is we have to find a value. So f of x is big O of x squared. On the other hand, f of x is also big O of x cubed. In this case, if we set m equal to 1 and x naught to 7, then 6x squared plus 7x minus 10 would always be less than or equal to x cubed. Again, so long as x was greater than or equal to 7. Again, where do those come from? From looking to see what values will make that relationship hold. As a non-example, we can show that f of x is not big O of x. So in this case, I wrote it in the set notation that it's not in the set. We could say f of x not equal to big O of x. If we look at what would happen, 6x squared plus 7x minus 10 being less than or equal to mx for all x greater than or equal to x naught would imply that 6x squared plus the quantity 7 minus m times x minus 10 is less than or equal to 0 for all those x values as well. We just subtracted m times x from both sides. So this would say that at a certain point, this 6x squared plus this number times x minus 10 is always negative. But we know that 6x squared is a parabola that opens upward. And so even if it has negative values, eventually it becomes positive and stays positive. And so there is no m that we can find that will work to make this thing always be negative. And so in this case, f of x is not big O of x, but it is big O of x squared, big O of x cubed, and so on. There's another notation that's really useful called theta notation. And it requires that f be bounded above and below by constant multiples of g. So f and g have the same growth rate. In the previous case, g could have the same growth rate as f, but the idea is that g grows faster than f. In this case, then, for theta, again, it's a set, and now we have three numbers. We have an m1, an m2, and the x naught. And in this case, the m1 goes with the lower bound, the m2 goes with the upper bound, and then that f is between these values for all x greater than or equal to x naught. And so in this case, our previous function f would be theta of n squared, but it would not be theta of n cubed. So theta is a more precise measurement. Often in the literature, you will see big O used in this context. So the big O is sometimes somewhat misused in terms of comparing two functions. And so theta is a more precise measurement. There are some other measures that are a bit more precise as well. There's a little o. There's an omega, a big omega, and a small omega that add a little more in terms of the preciseness that you can use to measure how fast one function grows. So when we're thinking about how fast a function grows, we can look at different rates. There's things that grow in constant terms. So we would have, like, say, big O of a number, big O of 1 is the way we typically write that. Or we could have theta of 1 if it is a constant. Then we have linear growth. We have quadratic algorithms that are, say, big O of n squared or theta of n squared, cubic, and so on. So all of these are polynomials. We also have things that are super polynomials. So exponential functions, say something that grows at a rate of, say, 2 to the nth power, or something that grows even faster, something that can grow, say, factorially or n to the nth power. And so all of these are other levels in terms of how much computation time is needed, or again, sometimes how much space is needed. So let's take a look at a particular example of an algorithm, and we want to find the largest. We're given a sequence of n numbers, and we want to find the largest value in this sequence. And so the first step is we need to get the values of the sequence, so we can't find the largest value without having the sequence of numbers. And so any algorithm that's going to find the largest will need to get the values in the sequence. So we'll have n storage locations for those values. So the approach that we're going to look at is we're going to set the value of a new variable called largest so far, and we're going to set it to the first value in the sequence. Now notice when we describe variable names in the mathematical context or the non-programming context, we don't necessarily use, say, a programming language criteria for naming variables. But we have this value of largest so far, and that's the first value because that's the first one we've seen, it's the only one we've seen, and at this point it is the biggest one that we've seen. So we can set the index to 0, that's the first, corresponds to the first value, or if we wanted to do this with a 1 index, we would set the index to 1. So again, that's a choice that we can make of what index we're starting. How are we going to count off the sequence of numbers? And so then we're going to repeat a process until all of the values in the sequence have been tested. And the process is we're going to get the current value in the sequence. And if the current value is greater than largest so far, we're going to update largest so far and set that equal to the current value. So we'll look at the first one. Okay, that's the largest so far that we have. Then we go to the next one. If it's bigger than the one we already have, we update. If not, we keep largest so far, and we go on to the next value. Now, we are keeping track of the index as well. If anytime we update the current value, anytime we update the largest so far with the current value, we're going to update the index because we're going to use that in the next algorithm that we have. So we might as well keep track of it at this point. So what do we have? Let's suppose that the largest value is the 8th position. We will update the largest so far at the beginning. Anytime along the way, we will update the largest so far if we run into a larger number, and we keep setting the index to the new update. If the current value is not greater than largest so far, then we don't do that update. When we finally get to the end of the sequence, then largest so far will be the largest value in the entire sequence. And so we would know largest so far is actually largest, and we would know the index of where that occurred. Now, since we only updated if it was greater than the largest so far, if there were multiple instances of the largest value, we would not know that. We would only recognize the first instance of the largest value and know where it was. And so at the end, once we've gone through all the values in the sequence, we output the largest so far. All right, so this algorithm will find the largest value. It's guaranteed to find the largest value, although we do actually would actually need to prove that this does what we expect it to do. But if we reason our way through, we can see that it's only updating when it finds something bigger than what we have found so far, and it stops when we get to the end. And so we have checked everything to see if it's bigger than anything we've seen before. So to analyze this, we want to think about the runtime. So when we're looking for the largest value, it's comparisons that we're doing. And so we want to count the comparisons. We don't really have to worry about things like updating the counter, updating the index value to increment to the next one. Okay, that happens. That is part of something that happens. But if you are looking at values in a sequence, you do, in any method, have to go from one number to the next to the next. And so it's really comparisons that are the issue in this algorithm. And so there are n-1 comparisons. We compare the first value to the second one, right? When we get to the second value, we compare that to largest so far. The very first value we don't compare, we just assign it to be largest so far, but then we compare everything else. So there are n-1 comparisons. And that's the case no matter what, best case, worst case, average case. And so this algorithm is a theta of n algorithm, or we just sometimes say the algorithm is theta of n. It actually requires that many comparisons. Again, the theta of n part disregards if there had been a coefficient on the n, and it disregards the -1 portion. Because what happens if we had 10,000 entries in our sequence, the -1 is inconsequential. If we had 100,000 or 1,000,000 or 10 billion, again, the -1 just doesn't really matter at that point. So again, the best case, the worst case, and the average case are all the same, because what does this algorithm have to do? It has to try every single value no matter what, because it doesn't know when it's going to find the biggest value. If it found the biggest value at the beginning, the algorithm doesn't know that until it has tested everything all the way through. So it doesn't matter where the biggest value is, the algorithm has to do the same amount of work to find that largest value. In terms of space, we need to store index and we need to store largest so far, and those are the only two values that we need to store. And so the space is constant space. We say that's big O of 1. It doesn't mean that there's one space, but that is the way we represent or describe a constant, because the amount of space is bounded above by a multiple of 1. And the multiple of 1 in this case is 2. We need a place to store the index. We need a place to store the largest so far. Now, if the largest so far was an extremely large number and we had to worry about other memory allocation, then it's a little bit more, we have to be a little more careful. But the basic idea is that there's only two values that we need to keep track of. And that then tells us that that particular algorithm doesn't use much space, and it checks every entry in the sequence only once. And so in terms of finding the largest, you can't really do much better than that. All right, so now let's take a look at another problem. And in this case, we have a sequence of numbers again. And instead of just finding the largest, we want to arrange them into increasing numerical order. So this is a sorting problem. And we're going to look at one particular sorting method called selection sort. But there are lots of sorting algorithms, and some being much better than others and some being not so good. But we're going to look at this particular method. So in this method, we get the values in the sequence again. We can't sort them without having them in place. And in this case, then we're going to put this marker at the end of the sequence. And we're going to say, okay, at the end of the sequence of numbers, we have an indication, a marker there that says anything after this has already been sorted. And it's at the end of the sequence right now because nothing has been sorted. And so what we're going to do is then we're going to do this until the sorted marker gets to 1. We're going to keep moving it to the right, or excuse me, moving it to the left until the sorted marker is beside the very first entry. Again, I'm thinking index 0 at this point. The sorted marker, when it's beside the very first entry, then everything after that will have been sorted. The thing before that then must be sorted because it's a single element. And so then the algorithm will conclude with everything in order. So what we're going to do is we're going to use our find largest algorithm to just get the largest value and its index. So that's what find largest did. It gave us the largest value and the index. We're going to swap that largest value with the value at the end of the list. So when we find the largest, we swap that value So we know where we're swapping to because we have the index. We're going to take the value at the end, no matter how big or small it was, and swap it with the largest. Then we're going to set the sorted marker to sorted marker -1 and output the ordered sequence. So to analyze selection sort, let's think about the runtime first. Again, comparisons are the primary operation. We are comparing values to find the largest, and then just doing swaps after that. The swaps aren't really that important because any method that is going to sort this sequence will do those swaps. So it's the comparisons that really matter. We're only going to focus on the comparisons. So to get the largest one in place, we do n-1 comparisons because that was the find largest on the entire sequence. Once the largest one overall is in place at the end, we've moved the marker back one, and so now we have a smaller list to consider. So when we find the largest of that, it's a smaller list, and so it's one fewer comparisons, and then we put the biggest one in place there, move the marker back, and keep doing that until we have two elements left. We find the biggest of those two, do the necessary swap if it's needed, and then the last element is automatically in place at the beginning of the list or the sequence. And so if we add up all those, n-1 plus n-2 plus all the way down to +1, then we get a quadratic, and so this algorithm is theta of n squared. Now, again, the best case, the worst case, and the average case are all the same. If they weren't all the same, then instead of talking about theta, we would be talking about big O, because we would be focusing on the worst case scenario. But in this case, all the cases are the same, that this is a quadratic. Now, if you remember adding up 1 plus 2 plus 3 all the way up to some value, say n-1, there's a formula for that. And the value is not exactly n squared, but as far as the big O or the theta calculation is concerned, this algorithm is theta of n squared. If we look at the space analysis, we store the index, we store the largest so far, and we store the sorted marker so that we know where things are. And then we overwrite the index and the largest so far. We keep reusing those. The sorted marker moves to the left as we progress through the algorithm. A very minimal amount of outside storage. And so again, we have constant space. So again, big O of 1 on the space in that case. So let's take a look at another problem. Given a sequence of n numbers arranged in increasing numerical order and some desired value, let's find the value in the sequence or determine that it's not there. So the idea is the number that we're looking for is hopefully in the sequence. We just don't know where, and our task is to find it, or to as efficiently as possible check through and find out that it's not in the sequence. So again, we get the values in the sequence, the length of the sequence, and the desired value. Then we're going to repeat a process until there are no values left to consider. What we're going to do is, first of all, we go to the median value in the sequence, the value that's in the middle. Except this isn't quite true because the median may not actually be an element in the sequence. The median could be in between. So we're going to go to the halfway mark, and if we need to shift to the left or to the right to stay with a value in the sequence, then we will do that. And usually we're going to shift to the left to stay in the sequence. But we go to the middle of the sequence, and then if that is the number we were looking for, the desired value, then we're going to output found, we found it, and we stop, we're done. The algorithm would terminate at this point. Otherwise, we're going to determine whether the desired value is less than or larger than our median value that we're looking at now. So you think about looking up a name, say, in a telephone book. You're trying to find a particular name. So you open the phone book, you know which name you're looking for, you see where you are in the book, and you either go earlier or later in the book, depending on whether you're at the right spot in terms of the right letter. Now, once you're on the right spot, then we have to look at where on the page and so on. So we're ignoring that feature of looking up something in this way. But the general idea here is we're going to keep going then to the middle. If the desired value is less than the median, we're going to throw away the bigger numbers and make the smaller set our sequence. And if the desired value is larger than the median, then we're going to throw away the smaller numbers. And so basically what's happening at each point is we're making we're checking, and then we're cutting the sequence in half and checking a much smaller set. And then deciding, are we on the left-hand side or the right-hand side of what's left? And throw away the part we don't want and keep doing that until we get down to there being no values left to consider. If we get down to no values being left to consider, that means that the number that we were looking for is not in the sequence. Otherwise, it will be one of the values when we get to a particular median and we get there, then that will be the value that we were looking for. And so if we get all the way through the process and don't find the value we're looking for, then that value was not in the sequence. Otherwise, we eventually will find it. And basically what we've done is taken possibly a large sequence and keep cutting it in half and cutting it in half and keep doing that until we find the value that we're looking for. And just as you know that doubling things gets big in a hurry, cutting things in half gets small in a hurry. And so that is a nice feature of binary search, that it can find the appropriate values rather quickly. So to see how quickly, let's do the runtime analysis of binary search. Again, it's comparisons that we're looking at. We're saying, is this value the value that we care about? Well, there are some calculations in terms of going to the midpoint of the sequence that we have at that point. But again, it's the comparisons that are the heavy lifting in the algorithm. And it turns out that in the absolute worst case, there are log base 2 of n plus 1 comparisons that are needed. Since we write log base 2 a lot in algorithm analysis, we often just write this as lg of n. As we write log without the base for log base 10, we write ln for the natural log. We often will write just lg for a log base 2. It doesn't really matter. We could write it as a log base 10. You can do a calculation to do the change of base, but it really is the base 2 because of the halving aspect that's going on here. Again, rounding things might be possible. We might have to round that up if the set is not a power of 2. So for this algorithm, we describe it as being big O of log n. So it's a logarithmic algorithm. And a logarithmic algorithm is slower than, it takes more time, let's think of it that way, it takes more time than a constant function, but less time than a linear function. So a log function grows very, very, very slowly. It does grow, but very, very slowly. In the case of binary search, the best case is if we found the number we were looking for right away, the very first guess that we made. When we went to the halfway mark the first time, if that was the right value, then the best case in this situation is big O of 1. So that's different than the other algorithms that we were looking at. Those were all the same in any case. In this situation, we have a best case and a worst case, and they do differ. As far as space is concerned, binary search just has to keep track of where are we looking, right? We have the values that were already given to us, and we calculate where are we looking, and we have to have a space to record that. But otherwise, no additional space really is required in this search algorithm. All right, now let's look at some things that are linear algebraic. Things are related to linear algebra, and the dot product is one. So we have two vectors of dimension n, and we want to calculate the dot product. And so to calculate the dot product with the runtime, we're going to look at the flops, so the multiplications and the additions that are necessary. So there are n multiplications and n minus 1 additions. If we do these separately, if we did this as an in place, then that would change the calculations just a little bit, where we would replace one of the vectors with the calculations as we're going. But in the case of vectors and the dot product, we're not going to replace things because the dot product is a number. With matrices, sometimes we might replace a calculation, or in other situations, we might replace values. So what do we have? We are going to do this multiplication, n multiplications, n minus 1 additions. So the total 2n minus 1 flops. And so this algorithm then is the same no matter what, so it's theta of n when we describe this dot product. Sometimes we keep track of the leading coefficient, and so sometimes you will see this kind of description written as big O of 2n. This is usually in numerical algorithms, and in that case we don't typically use the big O notation, but you will see that sometimes, so I wanted to share that with you. So the minus 1 is still disregarded. It doesn't really matter at all, but the coefficient does sometimes matter. The bigger the coefficient, then ultimately it can have an effect on when you choose which algorithm. So if one algorithm is 2n and another algorithm is 100n, then the 2n, although both are linear, the 2n is a much better choice than the 100n, provided there's no other issues that are going on. Sometimes the other issues are the 2n algorithm may need a whole lot of space, or the 2n algorithm may make some rounding choices that cause more errors in the long run, and so on. So there are other kinds of concerns. But usually when we're analyzing algorithms, we don't really worry about the coefficients at all. Sometimes with numerical algorithms, we do focus on them a little bit more. But again, not all of them, just the most important coefficient. So dot products are two vectors. We also could do matrix and vector multiplication. So we have an n by n matrix and an n-dimensional vector. We could have non-square matrices and work with those. The calculations are similar, so we're going to consider just the square matrix at this point. So runtime, what's going to happen? The conventional method says we calculate the dot product of each row of the matrix with the vector, and so we already know how many steps the dot product takes, and we do that once for each row. And so this conventional method for calculating a matrix times a vector is a theta of n squared algorithm. So there are n rows, and each one of those requires theta of n steps to carry out. There's another method called the fast Fourier transform, and some other methods as well, but I wanted to point this one out. it requires 8n times log n flops, which is considerably fewer calculations than the conventional method. At least when n gets big, it's considerably fewer. For small enough n, it isn't, but that doesn't matter. We're looking at what happens when n gets really big, if we had a really big matrix multiplied by a vector. So there are algorithms that are faster than the conventional method. Again, faster methods usually have other overhead and other conceptual or other difficulties in implementation. So there's some trade-off in that as well. If we just look at regular matrix multiplication, again, keeping these matrices squared, again, they don't have to be as long as the appropriate dimensions match, but just for the ease of analysis, we calculate the vector, calculate the matrix product. We would treat each column of B as a vector and complete the matrix vector multiplication n times. And so in this case, the conventional algorithm is theta of n cubed. There's another method that we will see a bit later called the Strassen matrix multiplication. It uses a block structure for the matrices and does the calculations and saves some. You can complete that method using about 7/8 of the multiplications and additions required by the conventional method. If you did the fast Fourier transform method, you can also get other improvements. There are some issues with all of these methods that, again, we do have to think about the size of the numbers that are involved in terms of just counting the multiplications. If the numbers get really, really big, then those multiplications become more, there's more to consider in terms of how big and how many bits there are in those values. Let's suppose we wanted to solve a triangular system. We're going to look at n equations with n variables in upper triangular form. And so we have n equations, n variables. So we have upper triangular form, though, means there's a lot of zeros in our matrix. And then we have the right-hand side of the equations. And so we're going to solve that the way we would typically expect using back substitution. If we have a 1 index in case, then the formula of, if a 1 index in place, the formula for this is in terms of the x values are, we're solving the system ax equals b. So we're calculating the x values. We have the b values, that's the right-hand side. And then we have all the values from the matrix. Those are the u values because it's an upper triangular matrix. And so the back substitution calculation is we do this calculation for each particular x value. In this case, since we don't need the b values anymore after we've done this, we can overwrite the b values with the appropriate new x value. And so we don't even need any extra space to do back substitution. If we're done with the right-hand side, if we're just trying to solve that system, and we don't need the right-hand side anymore, we can overwrite and replace it with our solution. As far as the runtime is concerned, there are n squared. Again, this is the big O version, floating point operations that take place during that. The multiplications, the subtractions, the divisions, all of those. This is a big O of n squared algorithm. And again, we already mentioned that no additional space is required since the calculations can be done in place. If you decided not to do those in place, if you wanted to keep B for future reference, then you would need n more storage positions, right, to store all the values that are in this n-dimensional solution to the system. Gaussian elimination is another way that we've seen to solve systems, but when you solve the system by Gaussian elimination, the first step is to usually turn it into an upper triangular matrix and then solve that matrix. So the addition or the extra work in Gaussian elimination is starting from a non-triangular system and turning it into a triangular system. And so we typically think of this as starting with an augmented coefficient matrix, so it's n rows and n plus 1 columns, turn it into an upper triangular matrix, and then use back substitution. And so in that case, we can go through very carefully and add up how many divisions and multiplications and subtractions are needed to do that. And in that case, it turns out to be an average of about 2n cubed over 3. So the number of operations is big O of n cubed. That incorporates both converting the matrix to triangular form and then doing the back substitution to solve the problem. If only integers or rational values are allowed to be used in the calculations, then bit complexity becomes an issue, and there's actually a big O of n to the 5th portion that comes into play. So sometimes you will see a more thorough analysis of Gaussian elimination. The thorough analysis includes what happens if the numbers are big and they're not incorporated using floating point arithmetic. If we're only using integers or rational values, then we're going for exact values, and that causes an extra that extra layer. If we are using floating point, then those are not exact, and so we include the concerns of round-off error and other kinds of problems that we've seen that can distort the appropriate value. Another algorithm that we might need, another problem that we need to solve is calculating a matrix inverse. If we have a matrix that we know has an inverse, then we want to find its inverse. If we didn't know that it had an inverse, then part of the problem would be determining that it does not. But there are multiple ways to calculate the inverse of a matrix. The Gauss-Jordan method, or probably one of the first methods that you saw before in calculating the inverse of a matrix, is we set up an augmented matrix with the matrix A on the left-hand side and the identity matrix on the right-hand side, and then go through the row operations until we get the identity on the left, and then A inverse is on the right. Now, in that method, in that procedure, if the matrix does not have an inverse, if it's a singular matrix, then we won't be able to create the identity on the left. And so in this case, the problem that we've been given, that it's a non-singular matrix, isn't even necessary using this particular method. And so since it involves the Gaussian elimination and maybe going a little bit further in terms of clearing things out, but this is, again, a cubic algorithm for calculating the inverse. There's another algorithm that's related to the Strussen multiplication, and that one requires big O of n to the 2.807 operations. And where that number comes from, we're not going to talk about, but that's better than n cubed. That's a smaller exponent. And if n gets big enough, there's a really big difference in terms of the two algorithms and the time involved in doing those. There are other methods with smaller exponents, but in those cases, the exponents that are hidden in the big O notation are larger and make the methods, at least in most cases, impractical in practice. So the amount of work ends up being more than it would have been with one of the other algorithms. Okay, so we've talked about some specific algorithms for various problems, but what if instead of focusing on the algorithm, we look at the overall problem, the problem itself? And so what happens in that case is the particular problem is maybe in one of, well, hopefully in one of two classes, we'll talk about that. The class P is the class of all the problems for which a polynomial time algorithm exists. Now, the polynomial time algorithm might have an exponent of 300, so be n to the 300th power. But as far as theoretically it's concerned, that is a better algorithm than something that is super polynomial. And so for class P, usually once someone finds a polynomial time algorithm for something, then it can be improved considerably rather quickly. So often a high degree polynomial is found, and then very readily that is exploited to make a lower degree polynomial. But like we saw with calculating the inverse, sometimes there's a bunch of work in going from an exponent of 3 to an exponent of 2.8. And to try to get that exponent even smaller is often an issue of a lot of work. And at a certain point, it becomes not so practical to get it smaller, but just the interest of what is the smallest that the exponent can be. So class P, all the problems we've talked about are in class P. There are polynomial time algorithms for solving each one of those problems. There are some problems that we can not find a polynomial time algorithm yet. We don't know whether one exists, but the class NP is the class of problems where a potential solution can be checked in polynomial time. So maybe not solved. We don't know for sure whether it can be solved in polynomial time, but a potential solution can be checked so that we know whether it's correct or not. And so there's an interesting interplay between can you solve the problem quickly versus can you check a potential solution quickly. And there are some problems that are very clear that we can solve quickly. And there are some problems that we don't know how to solve quickly, but are easy to check. So if somebody were to give us a potential solution, we could check to know whether that was a valid solution. So in studying algorithms, there's a lot of time spent considering the class P versus the class NP. And there's a famous problem of whether or not these are the same class. And if you can determine whether or not class P is equal to class NP, there's $1 million prize waiting for you. Don't waste your time focusing on it too much, because as a friend of mine has said, there's a lot easier ways to earn $1 million than trying to solve this problem. But there's a lot to be learned from considering the problems that we know are in the class NP. That we don't know whether there are polynomial time algorithms. So we can still learn a lot about the problems that we do care about by considering problems that are in some sense at least harder. Maybe not conceptually more difficult, but computationally possibly more difficult. Now, the tractable problems are all of the ones with a known polynomial time algorithm. And so if we know it has a polynomial time algorithm, that problem can be solved. Even if the amount of time is actually big for a big enough value of n, we know that in realistic size problems, it's something that we can handle. We can still maybe improve the implementation, improve some other features of it, but the problem is doable. With enough resources, we can handle that. Now, an intractable problem is a problem that is proven to have a super polynomial time algorithm. So it's known not to have a polynomial time algorithm. And so there are problems that are known to be intractable, that often the only way to solve them is to, by say, brute force your way through every possibility, and there are just too many possibilities to consider. In those cases, we can often solve simpler but still useful versions of the problem. So even though the problem itself is intractable, we can still do something about it. Another approach is to use heuristics, which are basically good guesses, good rules of thumb to solve a problem. And there's an approach of using probabilistic algorithms to solve problems. And so you can not necessarily solve the problem every time, but you can almost certainly get a solution. That's a legitimate mathematical approach to things. And then there are methods of approximation techniques where you find approximate solutions knowing that they're not correct, but maybe you can tell that they're within a certain percentage of being correct. So it's similar to ideas maybe from statistics where you do sampling and you don't know the real population mean, but you know that your guess is 95% likely to be within a certain margin of error or something like that, right? So approximation techniques can sometimes be helpful. Now, there are some intractable problems that you can't even approximate well. There's no proof, there's no guarantee that your approximation is good. So there are a lot of much more difficult problems. So the tractable problems, the intractable problems, those problems that are in the class NP that we can check quickly, but we don't know whether we can solve quickly. We don't know whether they're tractable or not. So there are some problems that are in an unknown state. They may be tractable, they may be intractable, but there are some that we know for sure are tractable and others that we know for sure are intractable. And so these problems that we don't know about, people spend a lot of time trying to solve those, trying to find good algorithms for solving those. And then at the end of all this, there are just some problems that are unsolvable, provably unsolvable problems. And luckily for us, we don't need to concern ourselves with those right now, but there are problems that are interesting that we would like to have solutions for, but just no solution exists. So this has been a bit of an introduction to some of the important issues of algorithm analysis, and we're going to continue and look at some more of these issues as we go further along. So as usual, feel free to ask questions in the comments, by email, or on Discord.